a spacecraft the size of a car, powered by fuel no bigger than a grain of sand, accelerating to speeds that make our fastest rockets look like they're standing still. This isn't some distant fantasy from a science fiction novel. Right now, at facilities around the world, scientists are trapping actual antimatter and making serious calculations about when we might launch our first antimatter-powered probe. The timeline? Possibly within your lifetime. But here's the catch. We're not talking about the gleaming starships of science fiction just yet. The path to antimatter propulsion is stranger, more dangerous, and more ingenious than anything Hollywood has imagined. Today we're diving into the real science of antimatter drives, from the quantum mechanics that make them possible to the exact engineering challenges that stand between us and our first launch. By the end, you'll understand why some of the smartest physicists and engineers believe that antimatter propulsion isn't just possible, it's inevitable.
Let's start with a sobering truth about our current space technology. Every rocket that's ever launched from Earth, from the Saturn V that carried humans to the moon to the latest SpaceX Falcon Heavy, relies on the same fundamental principle as a steam train from the 1800s. We're burning stuff for energy. Chemical combustion. It's primitive, it's inefficient, and it's holding us back.
When we talk about exploring the galaxy, about sending humans to other star systems, chemical rockets simply won't cut it. The problem is energy density. Chemical reactions involve rearranging the electrons around atoms, and while that releases energy, it's nowhere near the theoretical maximum. Even our best chemical fuels contain only a tiny fraction of the energy that their mass could theoretically provide, according to Einstein's famous equation, E equals mc squared. This is where antimatter enters the picture. In terms of energy per kilogram, the antimatter drive is about as efficient as you can get within the bounds of the laws of physics. It's a staple of science fiction for good reason, appearing in everything from Star Trek to Angels and Demons. But unlike warp drives and hyperspace jumps, antimatter propulsion doesn't require us to break the laws of physics. It just requires us to master some extraordinarily difficult engineering challenges.
The theoretical foundation for antimatter goes back to 1928, when physicist Paul Dirac was working to bring quantum mechanics into agreement with special relativity. In solving his equations, he discovered something unexpected: negative energy electrons. At first, this seemed like a mathematical quirk, perhaps an error. But Dirac took it seriously, and his equations predicted the existence of antimatter before anyone had ever seen it.
4 years later, in 1932, Carl Anderson was studying cosmic rays using a cloud chamber and a magnetic field. He noticed particles that looked exactly like electrons but curved the wrong way in the magnetic field. They had to be positively charged. These were Dirac's anti-electrons, which we now call positrons. This discovery proved that antimatter wasn't just mathematical speculation. It was real, and it was being created naturally in high-energy collisions all around us. So what is antimatter really? The most intuitive way to think about it is as the mirror image of regular matter. Every particle of matter has an antimatter counterpart. If matter is Superman, antimatter is Bizarro. If matter is Mario, antimatter is Wario. The same fundamental structure, but with certain properties flipped.
Antimatter is inevitable in the universe with the symmetries of ours. If we think of particles as swirls and vibrations in quantum fields, well, those fields can swirl and vibrate backwards. The laws of physics are almost completely symmetric if we flip all quantum charges to their opposites, or reflect everything to its mirror image, or if we reverse the flow of time. Antimatter represents charge reversed and mirror reflected matter, which can equivalently be thought of as time-reversed matter. This matter-antimatter symmetry has profound implications. It means you can produce particles of matter out of pure vacuum, as long as you also produce the corresponding particles of antimatter to balance everything out. Of course, you also need energy to account for the new mass, according to Einstein's equation. This process is called pair production, and it happens constantly in high-energy environments throughout the universe.
But if the laws of physics are symmetric in time, this process works backwards too. A matter-antimatter pair can be uncreated, annihilated, to produce energy. And here's where things get interesting for space propulsion. Take Einstein's equation, E equals mc squared. Take the mass, multiply it by the speed of light, which is already a very big number. Then multiply it by the speed of light again. You get an absolutely enormous number.
To put this in perspective, if you could annihilate an espresso cup full of matter with an equal amount of antimatter, you would get an explosion with the power of a modern hydrogen bomb. That's the ultimate energy-dense spaceship fuel. That's why physicists and engineers can't stop thinking about antimatter drives.
Of course, there are complications to using antimatter, or we would already be flying around with it, then probably blowing each other up with it too. The challenges fall into three main categories: creating antimatter in useful quantities, storing it safely, and harnessing it for rocket propulsion. Each of these problems is monumentally difficult, but none of them appears to be fundamentally impossible. Before we dive into those challenges, we need to dispel a common misconception. There's a frequently repeated statement that matter and antimatter annihilation releases pure energy. This sounds impressive, but it's not quite accurate. There's not really any such thing as pure energy. Energy is a property possessed by systems. It can take many forms: mass energy, kinetic energy, potential energy, thermal energy, and so on.
The most charitable interpretation of pure energy is energy that's easily accessible and usable. In that sense, mass energy is actually the least pure or free form, precisely because it's the most compact. And that mass energy isn't necessarily all liberated during annihilation. The annihilation process will often produce other massive particles, so some energy remains locked away in their mass. The idea of pure energy probably comes from electron-positron annihilation specifically. In that case, the incoming particles have such low masses that the energy they produce typically isn't enough to create other massive particles. Instead, they annihilate predominantly into photons, with the rare neutrino produced as well. The entire energy content of those photons can be captured pretty efficiently, at least in principle.
But here's a crucial point. For rocket propulsion, we really need momentum, not just energy. Rockets work by throwing stuff out the back as fast as possible so that momentum conservation accelerates us forward. It's Newton's third law in action. Although our annihilation photons from electron-positron pairs have plenty of energy, they're massless and so carry relatively little momentum compared to massive particles moving at the same speed. Also, very high energy photons, gamma rays, are extremely hard to direct efficiently. They'll pass through most materials, making them difficult to channel into a useful exhaust.
Ideally, we want to harness whatever energy we produce to blast massive particles out behind us. It's certainly possible to do that with the energy of electron-positron annihilation photons in an indirect manner, converting that radiation into electricity and using it to accelerate ions, for example. But this adds complexity and inefficiency to the system.
There's another issue with this high-efficiency type of annihilation, and that has to do with storage, which I'll address in more detail shortly. But all of these considerations are nudging us toward using more massive versions of antimatter to power our spaceship, specifically antiprotons and eventually antiatoms.
Massive antiparticles are much harder to create than positrons, but let's trace the history of what we've managed to produce. We had the positron in 1932.
The next antimatter particle discovered was 2,000 times heavier, the antiproton, in 1955. This was followed quickly by the discovery of the antineutron. Then scientists started producing antinuclei with antiprotons and antineutrons bound together, just like in regular atomic nuclei. First came antideuterium, then antitritium, then antihelium-4. More exotic antinuclei have followed, with the current record being something called antihyperhydrogen-4.
All of these heavier antiparticles are identified in the debris of high-energy particle collisions, which means they're both rare and difficult to capture. There are two fundamental steps to working with antimatter. First, slow the particle down, then trap it. These collision products start out moving extremely fast, often at a good fraction of light speed, and they're moving in random directions. So they need to be channeled and then decelerated without touching any matter, which would cause immediate annihilation.
The world leaders in antimatter trapping are at CERN's antiproton decelerator. It's essentially an anti-accelerator, using electric and magnetic fields to slow down antiprotons that have been created in high-energy collisions. This is an extraordinary technical achievement, requiring exquisite control over particle beams and magnetic fields.
Once slowed, the antiparticle needs to be trapped, and this is arguably the harder part. If antimatter touches matter, it annihilates. This fundamental fact means there's no such thing as an antimatter-resistant material container that isn't itself made of antimatter. The solution is a non-material container, which means a force field. This sounds like science fiction, but we're really just talking about electromagnetic fields, which offer good options for trapping both charged and uncharged antimatter.
The most famous containment device for charged antimatter is the Penning trap. In this device, electrodes at either end create an electric field that keeps charged particles in the middle along the axis, while a magnetic field along that same axis prevents any particles from drifting away in the radial direction. It's like a magnetic bottle with electric caps on the ends.
This is the technology used by the BASE collaboration at CERN, who have managed to store 100 antiprotons for a full year in their Penning trap. That's a remarkable achievement, demonstrating that long-term storage of antimatter is genuinely possible. But there's a problem with this approach for fuel storage.
Electromagnetic containment, like the Penning trap, relies on the antiparticle having a net electric charge. But that introduces a new challenge. Like charges repel each other. So if you try to store a large number of antiprotons or positrons together, they end up as a big, diffuse cloud, spreading out as far as the trap will allow them. This defeats the entire point of using antimatter as a compact, energy-dense fuel. If you want to keep the particles close together, you need a colossal electromagnetic field, which requires a similarly colossal antimatter containment device. Again, this defeats the point. This is why we can't just use positrons or just antiprotons as fuel for a practical antimatter drive.
Happily, there's a workaround. If you trap both positrons and antiprotons in, for example, a Penning trap, and then cool them down sufficiently, they'll combine into antihydrogen atoms. This is exactly analogous to how regular electrons and protons combine to form regular hydrogen atoms. The process has been demonstrated multiple times in laboratories around the world.
Of course, now you have a new problem. The resulting anti-atom is electrically neutral, and so it immediately escapes the Penning trap, which only works on charged particles. This is presumably a bad thing if you're trying to store antimatter. A more sophisticated trap is needed.
The current solution is to exploit the fact that the antihydrogen atom has a magnetic moment. It behaves like a tiny bar magnet. It will try to align with and move in the direction of a magnetic gradient. So if you create a magnetic field with a minimum value in all three dimensions, any antihydrogen in that field will move toward the minimum and get stuck there. This is called a magnetic minimum trap, or magnetic bottle.
Because the newly formed antihydrogen will immediately try to escape its penning trap, the magnetic minimum trap has to be superimposed directly over the penning trap. This creates an incredibly complex electromagnetic environment that requires precise calibration. Now, the magnetic minimum trap is far weaker than the penning trap, and so antihydrogen needs to be really cold, colder than around 1 Kelvin to have any chance of remaining trapped. That's just 1 degree above absolute zero.
Various novel methods, including laser cooling, are used to further chill this antihydrogen to these extreme temperatures. But despite best efforts, this whole process is still very inefficient. Only a tiny fraction of produced antiprotons and positrons end up being converted into captured antihydrogen atoms. It's also difficult to keep much of this stuff trapped for long periods. The current record is held by the Alpha collaboration at CERN. The team trapped 112 antiatoms for times ranging from 1/5 of a second up to 1,000 seconds. That's about 17 minutes for the longest-lived antiatoms.
That's not exactly long enough for an interstellar journey. But now that we have actual antihydrogen, even in these tiny quantities, a new possibility opens up. Antihydrogen is expected to behave essentially identically to regular hydrogen in terms of its bulk properties. And that means that if we have enough of it, it can undergo phase transitions into more useful forms. Regular hydrogen freezes at 14 Kelvin at atmospheric pressure, becoming a solid. The hope is that enough antihydrogen would solidify at that same temperature.
That's actually the dream for antimatter fuel storage. Antihydrogen ice fuel pellets suspended in magnetic fields, compact and relatively stable. This would solve both the storage density problem and potentially make antimatter easier to handle and transport. Of course, we're still many orders of magnitude away from producing enough antihydrogen to freeze it, but the physics suggest it should work.
So let's imagine we have our antimatter fuel, perhaps in the form of these frozen pellets of antihydrogen. How do we actually use it to propel a spacecraft? Let's walk through what happens when you bring regular hydrogen and antihydrogen together.
First, the electron and positron annihilate, producing high-energy gamma rays. This part is relatively straightforward and releases a substantial amount of energy. But the real action comes next. The proton-antiproton annihilation is far more complicated because we're really annihilating 3 quarks with 3 antiquarks. When the hydrogen and antihydrogen atoms come together, the individual quarks don't all annihilate at once. Only the first quark and antiquark to make contact actually annihilate directly.
They're likely to produce particles like gluons or W bosons, which in turn create more quarks and antiquarks. This fragments the 2 baryons into a shower of particles, predominantly things called pions. Sure enough, this is exactly how antiprotons were originally discovered in collision experiments by Segre and Chamberlain in 1955.
These pions give us one approach to antimatter propulsion. They can be used directly as our working mass, which is the technical term for the stuff you throw out the back for momentum exchange, to create thrust. This design concept is called a pion rocket. It's possible because the charged pions, which make up about 2/3 of the pions produced, can be channeled and directed by a magnetic field. You could imagine a magnetic nozzle that focuses these charged pions into a beam shooting out the back of your spacecraft.
Unfortunately, the energy released in hydrogen-antihydrogen annihilation doesn't all go into charged pions. A significant fraction ends up as neutral pions, gamma rays, and neutrinos that completely ignore magnetic fields. The neutral pions quickly decay into gamma rays themselves, and the neutrinos just pass through everything. If we really don't want to waste the energy from these neutral products, and we probably don't if we're going to all the trouble of making antimatter fuel, there are other ways to capture it.
One approach is to capture the photons and kinetic energy of all the particles to generate electricity. You could imagine surrounding your reaction chamber with materials that absorb gamma rays and convert their energy to heat, then use that heat to generate electricity through thermoelectric converters or heat engines. That electricity can then be used to accelerate other particles to provide thrust, as in an ion drive, which we already employ for very steady, if slow, acceleration in spacecraft today.
This approach can be used whether or not the annihilation products themselves are also used directly for propulsion, and that makes it also a viable option for electron-positron annihilation, where all the energy comes out as gamma rays in the first place. You're essentially using antimatter as an incredibly energy-dense battery to power an electric rocket.
So how long before we get our first antimatter craft? Well, quite a while for our first crewed interstellar craft, but maybe not so long for our first unmanned probe, especially for missions within our own solar system. That might be possible if we use antimatter in a sort of hybrid mode with nuclear fission or fusion.
Nuclear power has been proposed for space travel in a couple of different scenarios. The more conventional approach is to use a fission or fusion reactor, generating electricity to power an ion drive. A more radical approach, but actually perfectly within our technological grasp, is nuclear pulse propulsion, like the famous Orion project from the 1950s and 60s. In this concept, a series of fission or fusion bombs are detonated behind the ship or behind a large sail or pusher plate to propel it forward through repeated explosive impulses.
Both direct nuclear reactors and nuclear pulse propulsion suffer from the same fundamental challenge: the minimum size of the device needed. Fusion reactors need to be huge to sustain a reaction with net positive energy output. This is why, despite decades of research and billions in funding, we still don't have commercial fusion reactors generating electricity. Similarly, nuclear weapons need to be above a certain size in order to initiate their chain reaction. There's a minimum critical mass of fissile material required.
But what if a small amount of antimatter can be employed to kick off the reaction? Then these devices can be made much smaller, which opens up entirely new possibilities for spacecraft design.
Let's take the hydrogen bomb as an example. A key component of a thermonuclear weapon is some sort of fission core, typically a sphere of plutonium. This is surrounded by a layer of heavy hydrogen isotopes, deuterium and tritium. The plutonium is detonated as a fission bomb, providing the intense heat and neutron flux needed to ignite fusion in the surrounding hydrogen. This is the Teller-Ulam design that makes modern thermonuclear weapons possible.
Because of the need for a critical mass of plutonium, there's a minimum size for a hydrogen bomb, which translates to a minimum explosive output. That in turn means that any Orion-type spaceship needs to be pretty huge to capture and withstand that energy. The original Orion designs called for spacecraft weighing thousands of tons.
But what if we replace some or all of the plutonium core with a tiny grain of antimatter? Then we can build a much smaller device in the same basic style, with the annihilation of the antimatter providing the energy and particle bombardment needed to ignite a smaller fission core, or potentially even directly ignite fusion in the hydrogen fuel. Either way, this enables a more manageable thermonuclear explosion, which would work on a much smaller craft.
This approach is called antimatter-catalyzed nuclear pulse propulsion. More generally, antimatter-catalyzed fusion or fission may be useful in powering spacecraft in various ways. The main advantage of doing this is that we need far less antimatter because most of the energy still comes from the classical nuclear fuel, whether that's uranium, plutonium, or hydrogen isotopes. The amount of antimatter needed is as low as micrograms by some estimates.
Now, at current production rates, it will take us a few decades to produce even micrograms of antimatter. But then,
we could potentially build an antimatter-catalyzed fission craft that could reach the Oort cloud, which is farther than anything humanity has ever sent into space, and do it in a mere 10 years of travel time. At least, that's what one detailed proposal has calculated.
Other proposals for non-crewed craft using antimatter catalysis are also within distant but not science fiction level reach. It's remotely possible that the first antimatter-enabled launch will happen in some of our lifetimes. And this isn't all just theoretical speculation. Early experiments have already shown that antiprotons cause extreme amplification of fission in non-critical heavy metal samples. The physics works, we just need to scale it up.
So we started out wanting a not too disappointing alternative to the impossible faster-than-light drives of science fiction. What's it really going to take to build a proper antimatter drive like the ones we see in Star Trek? The main holdup is the rate at which we can produce and store antimatter. Once we can make enough to solidify into those frozen pellets we discussed, storage becomes somewhat easier. But at current rates, accumulating enough antimatter for a crewed interstellar mission is going to take centuries to millennia.
We can certainly build more and bigger particle colliders devoted just to antimatter harvesting. But there's also the intriguing possibility of harvesting antimatter in space itself. Space is full of high-energy cosmic rays, and those cosmic ray collisions are making antiprotons all the time. The Pamela satellite discovered that Earth's magnetic field actually confines antiprotons and positrons produced by those collisions in the Van Allen radiation belts. So maybe we could harvest this naturally occurring antimatter from the Van Allen belts to fuel up for an interstellar journey.
A side advantage to harvesting in space is safety. I'm not sure any of us would want to be blasting off from Earth's surface sitting on top of a stash of delicately suspended antimatter. One containment failure, and you've got a thermonuclear explosion at the launch pad. So that's where we stand with antimatter drives. They're not quite around the corner, but there are plausible paths to the first versions. And at least for those hybrid versions using antimatter catalysis, the technical challenges seem genuinely solvable with focused effort and funding. Our first crewed interstellar antimatter-powered spaceship is not in our lifetime. But if we want it to happen, if we commit the resources and maintain the effort, it will happen. One day, perhaps in the next century or two, we will cross the galaxy by annihilating the mirror reflections in the quantum symmetries of space-time itself. The fuel of the future is already here. We just need to figure out how to make enough of it.